In the previous video, we used matrices to solve systems of linear equations. Matrices, however, can be used to do much more than that. There is a rich mathematical theory of matrices, and its applications are numerous. In this video and the next, I will introduce some fundamentals of matrix theory. If m and n are positive integers, then an m by n matrix is a rectangular array in which each entry, a sub ij, of the matrix is a number, and m by n has m rows and n columns. It is standard mathematical convention to represent matrices in any of the following three ways. First, a matrix can be denoted by an uppercase letter such as A, B, C, and so on. A matrix can be denoted by a representative element enclosed in brackets such as A sub ij, B sub ij, and C sub ij. A matrix can be denoted by a rectangular array of numbers such as this one. Two matrices A and B are equal if they have the same size and the corresponding elements are also equal. For instance, consider the following matrix in example 3.1. Matrices A and B are not equal because they are of different size. Similarly, B and C are not equal. Matrices A and D are equal if and only if x is equal to 3. We call matrix B, which is a 2 by 1 matrix, as a column matrix, whereas matrix C, which is a 1 by 2 matrix, as a row matrix. We can also partition the matrix A into a 2-column matrix, A sub 1, which elements are 1, 3, and A sub 2, which elements are 2, 4. And we can write it as follows. Just like vectors, we can also perform addition and scalar multiplication to matrices. We defined matrix addition as given two matrices A and B, which size is m by n for both matrices. The sum, denoted by A plus B, is the m by n matrix, which elements are the sum of the corresponding elements of the two matrices. The sum of two matrices of different sizes is undefined. For example, suppose we want to add the two matrices in example 3.3. To do that, we simply add the corresponding elements of the matrices. That is, 1 plus 1 for the first element. Next, we have 0 plus negative 1 for this element. 2 plus 3 for this element, and 1 plus 2 for this element. We perform the operation and we have 0, negative 1, 5, and 3. Another example is example 3.4. Notice that the two matrices have different size. The first matrix is a 3 by 3 matrix, whereas the second matrix is a 3 by 2 matrix. Therefore, the sum of the two matrices is undefined. Next is scalar multiplication. We define scalar multiplication as given a matrix A, which is an m by n matrix, and a scalar C, then the scalar multiple of A by C, denoted by CA, is the m by n matrix generated by multiplying all the elements of the matrix A by the scalar C. For instance, consider example 3.5. Given the matrix below, perform the operation 3 times A. To do this, all we need to do is to multiply every element of matrix A by 3, which gives us 3, negative 9, 6, 6, 0, 3, 12, -3, and 6. With example 3.6, let's perform series of operations with matrices. Consider the two matrices A and B and perform 3 times A minus B. To do this, all we need to do is to multiply every element of A by 3 first. That is 3, -9, 6, 6, 0, 3, 12, -3, and 6. Then, negative B is equivalent to multiplying matrix B by -1. That is plus -1 times B. Or, in other words, subtracting all the elements of B from the corresponding elements of matrix A. That is 3 minus 2, because this is the first element of matrix B, -9 minus 1, 6 minus -1, 6 minus 0, 0 minus -4, this one, 3 minus 3, this one, 12 minus 0, -3 minus 3, and 6 minus 2. Perform the operation and we have the result. This is 1, this is -10, this is 7, this is 6, this is +4, this is 0, this is 12, this is -6, and this is +4. Similar to vector operations, matrix addition and scalar multiplication has its properties. The first one is commutative property of addition. Basically, when adding two matrices, switching the positions of matrices A and B will give us the same result. The second property is associative property of addition. This means that given three matrices, A, B, and C, regardless of order of operations, the result will be the same. Next is associative property of scalar multiplication. Multiplying the scalars C and D first, then multiplying the product to the matrix A is equal to the product of C and the product of scalar D and matrix A. Multiplicative identity means that multiplying 1 to matrix A will give us matrix A. Fourth is the distributive property over matrix addition. Adding the two matrix A and B, then multiplying the sum by scalar C is equal to the sum of the product of a C and matrix A and the product of C and matrix B. Finally, distributive property over scalar addition. Adding two scalars, then multiplying the sum to matrix A is equal to the sum of the product of C and A and the product of D and A. In addition to these properties, we have properties of zero matrices. Zero matrices are any m by n matrix which elements are all zero. Now, if we have an m by n matrix and a scalar C, the following properties are true. First, the sum of matrix A and an m by n zero matrix is equal to matrix A. Second, adding matrix A and matrix A times -1 will give us an m by n zero matrix. And finally, if the product of scalar C and matrix A is the zero matrix, then C is 0 or A is a zero matrix. That's it for our video. Thank you very much for watching and have a good day.